In this lesson, we're going to look at strong and weak acids and bases and how that's different from concentrated or dilute acids or bases. So if you recall, we are using Arrhenius's definitions of an acid and a base. So an acid is a substance that will ionize in water, and when it does that, it's going to produce one or more hydrogen ions. And a base is a substance that's going to dissociate in water to form one or more hydroxide ions. So if you recall, we had this visual to show that our acid, and we can use HCl as an example, is going to split or ionize into hydrogen ions and then chlorine ions. If I use sodium hydroxide as an example for the base, sodium hydroxide is going to dissociate into hydroxide and sodium ions. And recall that we also talked about the fact that hydrogen ions are not actually going to be found on their own, but they are going to end up combining with water molecules to produce what we call a hydronium ion. So percent ionization, what's that? That is the percent of molecules that are going to split into their ions. And so this is going to be the difference between a strong acid or a base and a weak acid or a base. So the percent ionization is just whatever we are starting with. So if I have an acid to start with, what percent of that acid is going to end up dissociating into the hydrogen ion and then the anion or the negative ion that was paired with that hydrogen to make that acid. So you can see here for a strong acid, everything in here is completely separated into the negative ions and the hydrogen ions, which of course are actually going to be hydronium as they combine with a water molecule. As we look at the weak acid, here we can see some acid that has not ionized. It hasn't split into the hydronium ion and the negative ion. So we can see some have and some have not. So this is going to be the difference between a strong and weak acid. So strong acids completely dissociate in water. Now, when we say completely dissociate, what we mean is 99% or higher. So near complete dissociation, if not complete. So we can see here at the beginning, hydrochloric acid is all one compound, and when it's in water, there's going to be complete dissociation. So all the bonds between hydrogen and chlorine have been broken, and we now have hydrogen or hydronium ions as they combine with the water and chlorine ions. Now, important note, if you are making acid a certain concentration from a stock solution, you always add acid to the water. If you add water to acid, to a very concentrated acid, then you can end up, there will be a lot of heat produced, and you can end up shattering the container it's in from the enormous amount of heat that is produced. So as a safety precaution, always add acid to water. Weak acids, on the other hand, these are not going to completely dissociate in water. So if I have acetic acid, which is hydrogen with an acetate attached to it, and we're using AC to represent acetate instead of C2H3O2, which is its formula in this diagram. So at the beginning, everything is bonded together. When it's in water, some will dissociate, some will not. So strong acids are going to completely ionize. So when we say that, we mean 99% or more of the molecules of acid will ionize. What that means is the concentration of hydrogen ions is going to be equal to the concentration of the acid. So the square brackets here represent concentration. So just a way that you can reduce the amount of writing. So instead of writing concentration of hydrogen ion or hydronium ion, we can just put square brackets around it, and that represents concentration. So because all of the acid is going to ionize, then our concentration of hydrogen is going to be equal to whatever our concentration of the acid was. So if I have a 1.2 mole per liter solution of hydrochloric acid, then once I have that in water, that means that I have 1.2 mole per liter of concentration of hydronium ions. Because I have so many ions in solution, that there's going to be a high electrical conductivity. The pH is going to be very low. So remember, acids are between 0 and just under 7. So 7 is neutral. So anything under 7 is acidic. The lower the number goes, closer to 0, the stronger that acid is. So pH stands for power of hydronium ion, which means the more hydronium or hydrogen ions there are, the stronger the acid, and the lower the number is going to be. And we'll look at calculations of that in the 4U course. So some examples of very strong acids are perchloric acid, chloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid. And remember, one of the properties of acids was that they were corrosive, especially with metals. And the reason that is because that hydrogen ion will react with metals. Strong bases, so similar idea here, where a strong base is going to result because it has 99% or higher dissociation in water. So ionic hydroxides, or hydroxides that will have a high ionization, are sodium hydroxide, potassium hydroxide, barium hydroxide. So once again, complete ionization or over 99%. Similarly here, the concentration of the hydroxide ion is going to equal the concentration of the base. So if I have a 1 mole per liter or 1 molar solution of sodium hydroxide, I will have a 1 mole per liter concentration of hydroxide ions in that solution. So same deal, high electrical conductivity because we have a lot of ions in the solution because of the complete ionization. And this time we're going to have a very high pH. So when we have a high pH, that is because we have a lot of hydroxide ions in the solution. And so because we have complete dissociation here, we are nearing the 14 end of the range. So weak acids here, we are talking about less than 50% ionization. So if you didn't notice, we don't tend to have acids or bases that will have between 50 and 99% dissociating when in water. So there's a very clear distinction between what is a weak acid and what is a strong acid. So strong acids are almost complete, 99% to complete dissociation, and we would call all of that complete. Weak acids are less than 50% ionization happening. So that means that if not all of the acid molecules are going to dissociate into hydrogen and the negative ion, then my concentration of hydronium ions is going to be less than whatever my concentration of acid is. So if I have a 1 mole per liter solution of acetic acid, which is vinegar, then I'm going to have less than 1 mole per liter concentration of hydronium ions because I will still have a certain amount of the acetic acid combined together as one molecule in that solution. So here, because there aren't as many ions in the solution, there will be a low electrical conductivity, and the pH is going to be less than 7, but it is going to be a higher number, closer to 7, not close to 0. So these are a lot safer to handle and also eat or drink. So a lot of the foods and drinks that we consume are acidic, so they are less than 7 for a pH, but we're not talking about a 0, 1, 2 pH. So those are going to be strong acids like hydrochloric acid which our stomach is producing mucus all of the time to coat our stomach to keep the acid from corroding or eating away at our stomach, at our actual stomach lining. So we've got a lining within there to keep it safe. And so the acid is constantly reacting with that mucus, and so our stomach is constantly producing more mucus to keep from that corrosion happening. So acetic acid, citric acid, and carbonic acid are all examples of weak acids. Weak bases, so similar idea, less than 50% ionization. Because we don't have a lot of ions in solution, there's a low electrical conductivity. The pH here is going to be greater than 7, but it's going to be close to that 7 value and not close to 14. Ammonia, sodium bicarbonate, or baking soda are examples of weak bases. And then last thing we want to cover is what's the difference between strong versus weak and concentrated versus dilute. So strong means that it doesn't matter how many molecules or moles of an acid you have in a particular volume, all of it will dissociate if it's strong, and if it's weak, then very little of it will dissociate. So the difference between that and concentrated and dilute is a concentrated solution just has a lot of that solute or the acid or base in a given volume, and a dilute solution would have very little. So if this is a concentrated and strong acid, then this solute would be split into its ions and not be the whole acid altogether. If this was a concentrated weak acid, then we would have a lot of molecules of the acid that are still the whole acid and some that are ionized and split. Dilute then means that we have very little in a given area. So if I have a strong acid that is dilute, then I have all ionized, so all split into, for example, hydrogen and chlorine ions, but not very many in a given area. And if it's a weak acid, then some of these would stay as the full molecule and some would be ionized. So that's the difference between strong and weak versus concentrated and dilute.